Volcano in southwest Iceland has erupted, releasing streams of lava from under the Earth's surface. It follows thousands of small earthquakes in the area over recent weeks.
Happening right now in Hawaii, one of the world's most active volcanoes is erupting.
In recent months, a series of low-magnitude earthquakes have been detected beneath Mount Adams in Washington state, a volcano that has remained largely dormant for over a millennium. So, what does this mean? Well, the USGS has warned that the Cascade Volcanoes are waking up. This is a huge deal. Is another major disaster on its way? And when it comes, what will be the scale of destruction? This is a biblical catastrophe in the making, and when the timer goes off, there will be no stopping it. Scared? You should be. But to get any sense of the situation, we must start from the beginning. The Cascade Volcanic Arc is stirring up again. Stretching from northern California to southern British Columbia, the Cascade Volcanic Arc holds a unique position in geological studies due to its activity and potential for devastation. Recent seismic activity beneath Mount Adams, for instance, has drawn fresh attention to the arc. This concern is not unfounded. Many people who witnessed the fury of Mount St. Helens only 4 decades back are still alive and can recount the horrors of that fateful day that claimed not only several human lives, but also caused lasting devastation. So, what is happening now? Is this uptick in tremors a fleeting anomaly? Or could it be a harbinger of more significant events to come? Unfortunately, we can't be sure enough. These are untamed and unpredictable powers of nature. They can unleash their wrath quickly, without warning. Historically, the Cascade Volcanic Arc has been the epicenter of catastrophic eruptions. Mount St. Helens, Mount Rainier, Mount Mazama, now Crater Lake, and others have left indelible marks on the landscape and communities. Naturally, the stakes are high for communities residing near these peaks. A major eruption in the Cascade Range could devastate local infrastructure, force mass evacuations, and disrupt air traffic across the Pacific Northwest and beyond. In addition, lahars, or volcanic mudflows, pose an especially grave threat to areas like the Puyallup Valley near Mount Rainier, where densely populated regions lie directly in potential flow paths. These risks drive the urgency behind ongoing research, as scientists strive to decode the signals of the Earth and provide timely warnings. The Cascade Volcanic Arc is a geological marvel that stretches from southern British Columbia in Canada to northern California in the United States. This 1,200-kilometer chain is a defining feature of the Pacific Northwest landscape. The arc is not just a collection of breathtaking peaks, but also a hotspot of geological activity, deeply intertwined with the tectonic forces shaping the region. Its towering stratovolcanoes, picturesque landscapes, and volatile nature make it a focal point for understanding volcanic processes and their broader implications. Among the notable volcanoes in the Cascade Volcanic Arc are some of the most iconic and historically significant peaks in North America. These peaks and stratovolcanoes, coupled with numerous smaller volcanic features, form a dynamic system that has profoundly shaped the region's history, environment, and culture. The Cascade Volcanic Arc is an integral component of the Pacific Ring of Fire, a horseshoe-shaped zone encircling the Pacific Ocean that is characterized by intense seismic and volcanic activity. This global geological phenomenon results from the movement and interaction of tectonic plates, with the Cascades specifically influenced by the subduction of the Juan de Fuca plate beneath the much larger North American plate. As the denser oceanic plate is forced under the continental plate, immense heat and pressure cause the mantle to melt, generating magma that rises to the surface. Over millions of years, this process has created the dramatic peaks and volcanic landscapes that define the Cascades today. The geological activity of the Cascade Volcanic Arc has given rise to over a dozen major stratovolcanoes and numerous smaller volcanic features, such as cinder cones, shield volcanoes, and lava domes. These formations are not just geological curiosities. They play critical roles in shaping the surrounding ecosystems and influencing local hydrology. Volcanic soils, rich in minerals, have contributed to the fertility of the region's agricultural lands, supporting crops ranging from vineyards in Oregon to orchards in Washington. The snow-capped peaks act as natural reservoirs, feeding rivers and aquifers that supply water to millions of people and sustaining diverse ecosystems that include old-growth forests, alpine meadows, and wetlands. However, these benefits come with inherent risks, as volcanic eruptions can disrupt ecosystems, contaminate water sources, and alter landscapes. Beyond their physical and ecological impacts, the volcanoes of the Cascade Volcanic Arc have a profound cultural and historical significance. Indigenous peoples have long regarded these peaks as sacred, incorporating them into myths, spiritual practices, and oral histories. Today, the mountains draw millions of visitors annually for hiking, skiing, and climbing, while also serving as natural laboratories for scientific research. Understanding the Cascades is thus essential for preparing communities to coexist with the Arc's unpredictable nature. Speaking of nature's unpredictability, let's take a look at what to expect. Volcanic activity and potential hazards. The towering peaks of the Cascade Range, while often tranquil and snow-covered, harbor dynamic and potentially hazardous processes beneath their surfaces. The Cascade volcanoes are classified as active, with several demonstrating periodic signs of unrest that remind scientists and nearby communities of the ever-present potential for eruptions. Volcanic eruptions in the Cascades are not a distant memory, but an ongoing reality. Although the region has seen periods of relative dormancy, the underlying tectonic forces driving volcanic activity remain active. The subduction of the Juan de Fuca plate beneath the North American plate continues to generate magma, fueling the potential for future eruptions. Unlike extinct volcanoes that no longer have a magma source, the Cascade volcanoes still show clear signs of activity, ranging from minor gas emissions to occasional seismic events. One of the most critical indicators of impending volcanic activity is the occurrence of earthquake swarms, which are clusters of small tremors that signify magma or fluids moving beneath the surface. These seismic events often precede eruptions and can serve as early warning signs. For instance, Mount St. Helens experienced a dramatic increase in earthquake activity in the weeks leading up to its catastrophic 1980 eruption. Ground deformation is another key sign, as the rising magma can cause the surface to bulge or shift. Scientists use satellite imagery and ground-based instruments to measure these subtle changes. Additionally, gas emissions from vents and fumaroles, such as sulfur dioxide or carbon dioxide, can signal changes in a volcano's magma chamber. Monitoring these emissions helps researchers assess the likelihood of an eruption and its potential scale. The 1980 eruption of Mount St. Helens stands as a stark reminder of the catastrophic potential of Cascade volcanoes. Before the eruption, the mountain was a picturesque peak in Washington state, attracting outdoor enthusiasts and photographers. However, the weeks leading up to May 18, 1980, revealed ominous signs of unrest. Earthquake swarms, ground swelling, and increased gas emissions all indicated that the volcano was reawakening. On the fateful day, a massive landslide, the largest in recorded history, triggered a lateral blast, releasing an explosive force equivalent to 24 megatons of TNT. Other historical eruptions in the Cascades further emphasize the region's volatility. Mount Rainier, for example, has a history of generating lahars, or destructive volcanic mudflows, that have reached as far as the Puget Sound lowlands. Mount Hood has experienced eruptive episodes over the past several centuries, with lava flows and pyroclastic activity shaping its structure. The potential hazards associated with Cascade volcanic activity extend beyond eruptions themselves. Ashfall can spread across hundreds of kilometers, affecting respiratory health, damaging infrastructure, and disrupting agriculture. Pyroclastic flows, which are fast-moving currents of hot gas and volcanic material, can obliterate anything in their path. Lahars can travel far from the volcano, inundating valleys and rivers with a slurry of volcanic debris and water. Today, advancements in volcanic monitoring and early warning systems provide critical tools for mitigating these risks. Networks of seismometers, GPS stations, and gas sensors offer real-time data, allowing scientists to detect signs of unrest and issue timely alerts. Public education campaigns and emergency preparedness plans aim to ensure that communities in the shadow of these volcanoes are ready to respond when the next eruption occurs. However, this is easier said than done. This became all too well obvious on a fateful day in 1980. The awakening of Mount St. Helens. Leading to the fateful day of May 18, 1980, the area surrounding Mount St. Helens was shaken by weeks of intense seismic activity, including an unusual series of earthquakes and ground swelling. By late March 1980, the first signs of magma movement appeared in the form of small eruptions and ash plumes. A growing bulge on the north flank of the mountain, caused by magma pushing upward, was expanding at an alarming rate of nearly 5 feet per day, making it clear that something extraordinary was underway. Despite these ominous signs, the scale of what was to come was entirely unexpected. Geologists predicted that a major eruption was possible, but the exact nature and timing of the event remained uncertain. Evacuation orders were issued for areas closest to the volcano, but enforcement was inconsistent, and some residents chose to return or remain in the danger zone. Among those who stayed were loggers, campers, and journalists, along with individuals like Harry R. Truman, the owner of a lodge at Spirit Lake. Truman, who had lived near the mountain for decades, dismissed the warnings, believing he was safe despite the growing evidence of an impending disaster. On the morning of May 18, 1980, Mount St. Helens delivered its devastating surprise. At 8:32 in the morning, a magnitude 5.1 earthquake struck directly beneath the volcano, triggering a massive landslide, the largest in recorded history. The entire north flank of the mountain collapsed, releasing the pressure that had been building within the magma chamber. This sudden release led to a catastrophic lateral blast, sending a cloud of superheated gas, ash, and rock racing outward. The blast obliterated everything within a 230 square mile area, leveling forests, flattening buildings, and devastating Spirit Lake. Ash was ejected 15 miles into the atmosphere, darkening skies as far away as Spokane, Washington, and traveling across the United States in the days that followed. Pyroclastic flows, lahars, and falling ash created widespread chaos and destruction, claiming 57 lives and causing over $1 billion in damages. Many of those who returned to the area before the eruption underestimated the volcano's potential for destruction. Some believed that the warnings were exaggerated, while others thought they could leave quickly if the situation worsened. Tragically, the sudden and unprecedented nature of the eruption left no time for escape. The blast's lateral nature, rather than the expected vertical explosion, caught even scientists off guard. The aftermath of the eruption led to significant changes in how volcanoes are studied and monitored. The event spurred advancements in volcanic science, including the development of more sophisticated monitoring tools and the establishment of the United States Geological Survey's Cascade Volcano Observatory. However, to everyone's relief, in the years that followed, Mount St. Helens seemed to enter a period of relative dormancy, but this too was a ruse. In 2004, the volcano surprised the scientific community with a reawakening. This reawakening began in early September 2004, when scientists monitoring the volcano detected unusual seismic activity, including a significant increase in small earthquakes in the area around the volcano. These tremors were followed by noticeable ground movement, suggesting that magma might be rising beneath the surface. The area around Mount St. Helens began to exhibit signs of deformation, with the ground swelling as magma slowly accumulated beneath the surface, adding pressure to the region's geologic structure. By September 23, 2004, the seismic activity intensified significantly, and the pace of earthquakes increased. This escalation caught the attention of the United States Geological Survey and the Pacific Northwest Seismic Network, which immediately began to closely monitor the situation. As the weeks progressed, more signs of volcanic unrest became apparent. On October 1, 2004, the volcano showed the first dramatic physical sign of its return to life. A rift opened in the crater, and steam began to vent from the volcano, accompanied by smaller eruptions of ash and gas. Although this was not a catastrophic event like the 1980 eruption, it was significant in its own right. The small eruption provided a stark reminder of the volcano's power and its ability to produce explosive activity even after decades of dormancy. Today, we know that the volcano was never dormant. It could back then, and can in the present, reawaken with minimal warning. While advancements in volcanic monitoring have made it possible to predict eruptions with greater accuracy, there is still much to learn about how volcanoes behave and how to detect the early signs of volcanic unrest. But that's not all. The threat is not over just yet. The threat of volcanic eruptions in the Cascade Range is far from over, and the importance of continuous, advanced monitoring cannot be overstated. The region's active volcanoes, including Mount St. Helens, Mount Rainier and Mount Hood remain under close scrutiny by geologists and volcanologists to detect any signs of impending eruptions. The complexity of volcanic behavior means that these volcanoes can shift from periods of dormancy to sudden activity with little warning. To address this risk, scientists rely on an array of cutting-edge technologies to closely monitor seismic, volcanic, and ground activity. Advanced techniques, such as radar interferometry, satellite scans, and GPS stations, are central to these efforts, offering precision in tracking subtle movements in the Earth's crust that can indicate volcanic unrest. Radar interferometry, for example, uses radar signals sent from satellites or ground-based instruments to map surface deformations with incredible accuracy. By measuring the changes in the distance between the ground and the radar, scientists can detect the slightest shifts in the surface caused by magma movements beneath the volcano. These changes can be minuscule, yet over time, they can reveal important patterns and help predict whether magma is rising toward the surface. Satellite scans also provide essential data, offering a broader view of the volcanic landscape and enabling scientists to detect any subtle atmospheric changes, such as gas emissions, which are indicative of an impending eruption. These technologies work together to provide a comprehensive view of the volcano's activity. Moreover, GPS networks installed around volcanoes offer real-time data on the movement of the Earth's surface. By measuring changes in the position of the GPS units, scientists can track the slow but steady rise or fall of the ground, which often signals the movement of magma beneath the volcano. Even tiny shifts on the order of millimeters can provide critical information about magma migration and the potential for volcanic activity. These precise measurements enable geologists to gauge the pace and scale of volcanic unrest and predict whether the movements will lead to a full-scale eruption. One of the key sites being monitored closely is the Three Sisters Volcanic Center in Oregon, which is part of the Cascade Volcanic Arc. The area exhibits signs of increased ground uplift, which is a common indicator of volcanic activity. Steady ground deformation, particularly in regions where magma is rising beneath the surface, can point to increased pressure building up within the Earth's crust. This phenomenon, known as ground uplift, occurs when magma pushes against the surrounding rock, causing the land surface to slowly rise. While this type of activity does not always result in an eruption, it is a strong signal that magma is accumulating in the region, and the area is at risk of future volcanic activity. Understanding these early signs of unrest is critical for accurate eruption forecasting. However, despite the advancements in monitoring technology, conducting ground surveys in remote areas remains a challenge. Many of the most active volcanoes in the Cascade Range are located in difficult-to-reach wilderness areas, where access for scientists can be limited. Monitoring in these regions often requires the use of specialized equipment, such as drones, to collect data from places that are otherwise inaccessible. This remote nature can make it harder to track developments in real time, yet the ongoing research in these areas remains critical. As a result, scientists continue to refine their monitoring techniques to ensure that they can detect any potential volcanic hazards as early as possible, even in the most isolated regions. However, even with all this, eruptions can still catch experts by surprise. This is exactly what happened in 1989. After 30 years of dormancy, the Redoubt volcano erupted in 1989 with little warning. It surprised both scientists and residents with a sudden and explosive eruption that was triggered by a swarm of earthquakes in the area. The series of earthquakes that preceded the eruption was subtle enough that the volcanic activity was not immediately recognized as a sign of impending eruption. However, once the swarm intensified, scientists began to pay closer attention to the signals coming from the volcano. Within 24 hours of the earthquake swarm, Redoubt erupted explosively, sending ash plumes up to 60,000 feet in the air and disrupting air travel across Alaska. The eruption also sent pyroclastic flows down the volcano's flanks, impacting nearby communities and infrastructure. The eruption shows just how quickly a volcano can shift from dormancy to catastrophic eruption in response to seismic events. Redoubt's eruption stands in contrast to the more prolonged warning period seen before the eruption of Mount St. Helens in 1980. Mount St. Helens, which had been dormant for over 123 years before its catastrophic eruption, provided scientists with a 2-month window of warning. The eruption was preceded by significant seismic activity, including a series of small earthquakes, ground deformation, and gas emissions that signaled an impending eruption. These early signs allowed scientists to warn residents and prepare for the eruption, which ultimately occurred on May 18, 1980. While the warning period for Mount St. Helens was relatively lengthy compared to Redoubt's sudden eruption, the event itself was no less catastrophic. The eruption of Mount St. Helens involved the collapse of the volcano's north flank in a massive landslide, which triggered a violent explosion. In comparison, Redoubt's eruption, though explosive, did not involve the same dramatic collapse as Mount St. Helens. The volcano's eruption primarily involved the emission of ash and pyroclastic flows, rather than the massive landslide that characterized St. Helens. However, both eruptions demonstrate how volcanoes, even after periods of dormancy, can exhibit a wide range of eruption styles and behaviors. These catastrophic events highlight the importance of constant monitoring and the need for early warning systems that can detect subtle changes in seismic activity, ground deformation, and gas emissions. With these tools, scientists can better assess the likelihood of an eruption and provide warnings to mitigate the potential dangers posed by these unpredictable natural events. So, what have we learned so far? Lessons from the 1980 eruption of Mount St. Helens. When Mount St. Helens erupted with all its fury, scientific understanding of volcanic eruptions was still in its early stages, and the tools available to researchers were basic at best. Seismographs were rudimentary, and the scientific community had little more than binoculars and boots on the ground to observe the ongoing unrest. Despite these limited resources, Mount St. Helens had shown increasing signs of volcanic activity in the months leading up to the eruption, including seismic tremors, ground deformation, and steam eruptions, all of which indicated that something catastrophic could be looming. Yet, the scale and suddenness of the eruption were far beyond what scientists had predicted. The eruption on May 18, 1980, was a wake-up call for volcanologists worldwide. It provided an unexpected but critical lesson in volcanic science. It became evident that Mount St. Helens had a long history of explosive eruptions, but the scale of the event was unprecedented in modern times. As scientists began to investigate the eruption's aftermath, they uncovered evidence of past landslides and explosions within the crater, suggesting that Mount St. Helens had been capable of far more destructive events than had been previously realized. This discovery pushed the boundaries of knowledge about the dynamics of volcanic eruptions and spurred new investigations into understanding such catastrophic events. One of the most significant consequences of the eruption was the profound shift in how both the scientific community and the general public viewed volcanic hazards. The eruption's sudden onset and the massive destruction it caused led to an increased public demand for better volcanic monitoring systems. People wanted to understand more clearly when, where, and how eruptions might occur. This demand led to significant investments in more advanced monitoring equipment, including real-time seismic monitoring, advanced satellite imaging, and thermal imaging technologies. These tools would later play a critical role in detecting early signs of volcanic unrest in other regions, including the Cascades and beyond. The aftermath of Mount St. Helens also revealed a gap in the preparedness and response systems for volcanic disasters. The eruption occurred with limited warning, despite the signs of volcanic unrest, and the loss of life was tragic. It became clear that to protect lives and mitigate the impacts of future eruptions, scientists would need to develop more accurate prediction models and more efficient public communication strategies. In the decades since the eruption, Mount St. Helens has remained an active site of scientific research. Continuous monitoring of the volcano has improved our understanding of how volcanoes behave and what warning signs precede eruptions. What started as a catastrophe has since catalyzed advances in volcanic science, laying the groundwork for better preparedness for future eruptions. But this is no walk in the park. Dangers and challenges of volcanic research. Volcanic research, particularly in the Cascades, presents a unique set of dangers and challenges. The high temperatures, volatile conditions, and treacherous landscapes make volcanoes both awe-inspiring and perilous to study. Modern technology plays a pivotal role in volcanic research, but even with advanced tools, scientists face significant hurdles when monitoring these volatile environments. One of the most critical issues in volcanic research is the damage that extreme heat can inflict on equipment. Instruments including SPIDER, which is short for seismic pressure, infrared data equipment and research, are commonly deployed in active volcanic zones to gather crucial data. However, these devices are not impervious to the intense environmental conditions they are exposed to. The heat emanating from magma and volcanic activity often leads to the melting of plastic components, the burning of cables, and the shattering of sensors. These failures are not only costly in terms of lost equipment, but also can impede the accuracy and timeliness of data collection. Another significant concern for scientists monitoring volcanic activity is the presence of ice inside the volcano, which can melt as magma rises toward the surface. This phenomenon is particularly relevant for volcanoes located in colder regions, such as Mount St. Helens, Mount Rainier, and other Cascade volcanoes. As magma rises, it generates tremendous heat, causing ice and snow within the volcano to melt. The resulting pools of water, trapped in underground chambers or at the surface, pose a dangerous risk. If the conditions are right, these water bodies can trigger steam-driven explosions. This sudden release of steam can be catastrophic, sending debris flying at high velocities and creating secondary hazards such as pyroclastic flows and ash clouds. The interaction of magma with water is one of the most volatile and unpredictable aspects of volcanic eruptions. To mitigate the risks associated with the physical exploration of active volcanic zones, remote monitoring has become the preferred method for gathering data. Satellites, drones, seismic instruments, and ground-based sensors are often deployed to study volcanic activity from a safe distance. These technologies allow researchers to track seismic tremors, measure ground deformation, monitor gas emissions, and observe thermal activity without putting themselves at direct risk. Remote monitoring provides valuable insights into the state of volcanoes without the need for scientists to venture into dangerous areas. However, the limitations of these technologies, such as resolution and range, mean that scientists still rely on a combination of methods to understand the full scope of volcanic behavior. Yet, even with remote monitoring, some challenges remain. The ability to access volcanic craters during certain times of the year is severely restricted due to weather conditions, particularly during fall and winter. During these colder months, the region's volcanic landscapes become treacherous, as snow, ice, and freezing temperatures make exploration both difficult and dangerous. The long nights of winter reduce the window of opportunity for fieldwork, further complicating data collection efforts. Snow and ice accumulation can obscure crucial signs of volcanic unrest, making it harder to detect early warning signs like ground movement or changes in gas emissions. Moreover, these challenging weather conditions also affect the safety of researchers who are tasked with setting up and maintaining equipment in the field. Even with the advancements in technology, human intervention is sometimes necessary to repair equipment, install new sensors, or take ground-based readings, and these tasks are fraught with risks. But the complications don't end here. Predicting volcanic activity is not easy. Despite decades of technological advancements and continuous research, the unpredictability of volcanoes persists. This, combined with the immense power they can unleash, makes any attempt at forecasting a high-stakes challenge. One of the cornerstones of modern volcanic research is the continuous 24/7 monitoring of active volcanoes. For instance, Mount St. Helens is widely regarded as the most wired volcano in the world because it is equipped with an extensive network of sensors and monitoring equipment. Scientists can track its activity through an array of sensors that provide data in real time. These advancements have led to a deeper understanding of the volcano's behavior, allowing researchers to detect seismic swarms, ground deformation, and gas emissions with greater precision. The continuous data flow helps scientists assess whether minor tremors are precursors to a more significant eruption or just normal volcanic activity, enhancing the capacity to issue timely warnings. Despite the advancements in monitoring and data collection, predicting which volcano will erupt next remains a difficult task. The process involves not just identifying volcanoes showing signs of unrest, but also determining the level of threat posed by each volcano. Scientists must consider multiple factors, including the type of volcanic system, historical eruption patterns, the location of seismic activity, and deformation levels. These factors help in estimating the likelihood of an eruption, but cannot guarantee a precise timeline. For example, Mount Rainier, one of the most active volcanoes in the Cascade Range, presents a particular challenge. Its proximity to urban centers like Seattle and Tacoma increases the stakes for accurate prediction. The potential for significant loss of life and damage to infrastructure is high if the volcano were to erupt, making it critical for authorities to have access to the best possible forecasts. However, predicting eruptions for volcanoes like Mount Rainier remains a challenge. This brings us to the recent tremors. While such seismic activity might appear minor or routine, history has shown that even subtle signs can precede catastrophic events. After all, the 1980 Mount St. Helens eruption began with similar unrest. Ignoring these tremors risks underestimating the potential for future eruptions, which could devastate communities, disrupt ecosystems, and challenge emergency preparedness efforts. By staying attuned to these warning signals, advancing our monitoring technologies, and fostering public awareness, we can mitigate risks and better prepare for any possible situation. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.